Hey guys, so for PA3, the first thing you have to do is implement your own semaphore. So in this video, I'm going to talk about semaphores, just to make sure that you guys understand what they are and what the different values might mean and how you might go about implementing them. This is also kind of useful if you're studying for the midterm and you're not quite sure on what semaphores are. So at a very high level view, you can think of a semaphore as a guard. And I'm just going to give him a hat to distinguish him as a guard. And this guard is guarding some room. Okay? And maybe they have a counter, like one of those little counters with 2 buttons. And then the counter starts with some value, like 3. And that value is how many people are allowed in the room at the same time. And because the guard can't see into the room, he's going to keep track of the people that are coming in and out with this counter. Okay? So for example, suppose the first person comes in, the guard is going to decrement the counter with this button, and person 1 gets to go inside the room. And so now the counter would say like 2. Okay? And then same thing if a second person comes in, now the counter is 1. And then if a third person comes in, now the counter is 0. Okay, so now the counter is 0, and that means that no one else can go into the room. So what's going to happen if a 4th person comes in? They're going to have to wait in line. And the guard's going to stop them from going in. Same thing if a 5th or a 6th person come in. They're going to have to wait in the line. Okay. Now let's assume that the second person decides they want to leave the room. Okay? So then the guard's going to press this plus button on their counter. The count's going to go to 1. So that means that one more person can go through, and he's going to let the first one in line go, which was person 4. And then the count goes back to 0, because the room's full again. Okay? So that's kind of at a very high level how you can think of semaphores. The slides also explain it in a gate, with a gate example. That's another good example. This is just a different one. So then, just to keep things clear, our semaphore is the guard, and the room is our critical section. And we want to control how many people, or in our case processes, can go inside this critical section. And I'm just going to abbreviate that CS, because I'm going to be talking about those a lot. And the idea here is that we want to protect or guard this critical section. Okay. So how can we go about actually implementing these semaphores? Like how do they work? And for this I'm looking at slides 16 and 19 of the lecture on synchronization, which I think is lecture 5, if I'm not mistaken. But the one about synchronization, basically. Okay? So there are 2 main methods that are associated with semaphores. Wait, and that'll take in some semaphore and some process ID. And this is called whenever a process wants to ask permission to enter a room. So called by process who wants to enter the critical section. Okay? And then we also have signal that also takes in some semaphore and some PID. And this one's called by a process when they're leaving the room. So they can notify our semaphore or our guard that they're leaving the critical section. Once, 2, exit. Critical section. Critical section. Critical section. Okay. Cool. So, what do we do with these methods? Like, what are they supposed to actually do? So, the first thing wait's going to do, just like our slides say, is decrement the value associated with the semaphore. And the value is kind of like the counter that the guard had. Value of sum. Okay, so if we start constructing kind of a high-level view of what a semaphore object or a semaphore struct in you guys' case might look like, we might want them to have a value. And this is some sort of int. And then your intuition should tell you that initially this value is, however, it represents how many processes can enter the critical section, can be inside the critical section all at once. So if you remember in our example, we initialized our counter to 3, and at any point in time there were always a maximum of 3 processes or 3 people in our room. Okay, so that's kind of how you can think about what does the initial value mean. And then during execution, this value is going to represent how many more processes can enter the critical section. So in our example, when the first person came through, our counter became 2, and that's because 2 more people could be inside our room, because 1 was already in there and our max is 3. So during execution, the value of the semaphore is how many more processes can enter this critical section. Okay? So that's kind of our intuition for what this value field, and this thing is going to be some sort of int or a number. Okay, so inside wait, the first thing we want to do is decrement that value, because 1 less person is going to be able to come in. And then we want to check if the value turned negative, then we want to block this process. Why might we want to do that? Well, if the value was 0 at the beginning of wait, then we decrement. That meant that no more processes could go through, remember? Because the value is how many more processes can enter, and 0 means no more can enter. So if it was 0, we decrement that value, so it would become -1, and -1 is less than 0. So that means we want to block that process from entering. We want to make it wait in line. So we block PID, and this part is really important, and a lot of people forget it. We want to associate it or link it to the semaphore. So each semaphore, because you might have more than one in a single program, regarding different rooms, different critical sections, each semaphore needs to keep track of its own queue of processes, its own list of waiting processes, so that it can restart them later when it has more room, or when other processes enter the critical section. So we go back up to kind of our high-level view of what a struct might look like. It will have a value, and it might also have a list. In your guys' case, it might be an array of blocked processes. So that it needs to know who it has blocked, so that it can restart it or unblock it later. So it can let it in later, basically. So list of blocked procs. Okay, and instead of a list, we might want to do a queue, because a queue will give us FIFO order, right? The first process that stood in line is the first one that goes in. I think the slides say that you can pick any process, but FIFO order is a pretty good policy to go by. It's pretty fair. Okay? Cool. So, we block it and we associate to the semaphore. If the value is greater than or equal to 0, that means that the process can go through, so we don't block it. We don't really do anything. We let the method finish. Okay, so what about signal? Well, we know that signal is called when a process wants to exit, so that means that one less process is going to be inside the critical section. So we want to increment the value of sem, right? Because one more process is going to be allowed to come in. And then if there are any blocked processes for this semaphore, right? We might have more than one semaphore, but for this specific one, if there are any blocked processes, we want to unblock one of them. And that's where this list or this queue of blocked processes comes in handy. Okay, and then just to reiterate, like I said, doing this unblocking in FIFO order is a good policy. And I think it's what we tell you to do in the assignment. Okay, so this is kind of at a high level what weight and signal should be doing. Let's look at some, so a question a lot of people generally have is, well, what should I initialize my semaphore to? Initialize sems value. Should it be 1? Should it be 0? Should it be more than 1? Should it be negative? Like what's a good initial value? And there's no like set good initial value. It's not always going to be 1, it's not always going to be 5, and it's not always going to be 0 or negative or something like that. It depends kind of on your situation. So I'll just go through a couple of examples of different initial values and what they mean, just to make sure that you guys understand what the different initial values mean. So if we initialize sem to 1, and then we have our critical section, so there's a weight, and then there's some stuff, and then there's a signal. Okay. This here, since we initialized it to 1, that means that only one process can enter the critical section at once. Can be inside critical section at once. Another way to think about it is only one process, and this is supposed to be a 1, can access a resource. At once. Okay, and what might be a good example of this? Let's suppose you have an ATM. Okay, and buttons, and it has the slots, and it's an ATM. Okay? An ATM is something that only one person can use at a time. You can't have two people both trying to get money out of an ATM, right? And so that's the kind of resource that only one person can access at once. So you might have your one person, and then your semaphore or your guard is going to be stopping anyone else who wants to access the ATM, and they're going to have to wait in line until you're done, or whoever's using it is done. Then this person finishes, they get their money, and a new person can come in. And it's only one person or one process at a time. And then another way another thing we call this is this concept of just one at a time is mutual exclusion. Because we do this so frequently, we a lot of times we have a resource that only one process can access at a time. We have a special name for it, and it's just mutual exclusion. Okay, but it's this idea of just one at a time. You can't have two or more. Just one. Okay, so that's one example. Now, what if I initialize my semaphore to some number that's greater than 1? Let's initialize it to 5. And then we have a critical section. Remember, critical sections start with a weight, because that means you want to enter the critical section. Then there's some stuff, and then there's a signal. Okay, so this means that 5 processes can enter the critical section at a time. Okay, so a very good example of this, and one that you guys are all really familiar with, is registering for classes. So you have a class, this is a professor, okay, and let's assume in this class it's really small, so you have 5 seats. Okay, and then you can have at most 5 students here. Okay, so that means that our semaphore is going to stop any new students from entering the class because the class is full until one of the students currently in the class leaves. So we can call this our wait list. And only when one of the students in the class drops can one of the students in the wait list be allowed to register. Okay, and it's the same, so this could be controlled by a semaphore, right? Only 5 people can be in the class. Any people after that have to be blocked and wait until some of the people in the class decide that they don't want to take the class anymore. And so when you initialize the semaphore to a value that's greater than 1, it means that you have a limit on how many processes can share the resource or enter the critical section or be in the class. But once you reach that limit, no more can go in, no more can go through. Okay, cool. What's another common example? What if we initialize our semaphore to 0? Now this example is a little different. Here, the first process that calls wait is going to block. So it's not like before where we had some limit, but either the first process or the first 5 processes or the first something processes would be allowed to pass through wait, and then the rest would block at wait. Here, the very first one is going to block at wait, and so we had to have a slightly different scenario. So for example, suppose we have a process 1, and process 1 is going to do some stuff, and then it's going to call wait, and then it's going to do some more stuff. Okay, and then we have a process 2, and process 2 is going to do some stuff, and then it's going to call signal, and it's going to do some stuff. So it's not like this room kind of scenario anymore, where you wait to enter the room and you signal to exit the room. Now it's more of a process 1 is going to call wait, and this wait is going to block until process 2 calls signal. So in this example, process 1 will wait for process 2 to do whatever it needs to do before it can signal. Alright, so it's more of a general synchronization example. Like, one process is going to have to wait for another one to tell it that it can continue, basically. And so, what's a good example of this? Suppose you have a music concert, and so you're going to be playing in your concert, and you have all your instruments, okay, and you have, I don't know, guitar and a keyboard. Okay, cool. So we have our our rock band and the musician. So maybe process 2 is like the roadies, right? No. Roadies. And so the roadies are the people who are going to be setting up all the instruments so that the musician can play. And then the musician is going to have to wait. He's going to be blocked by a guard until the roadie says that the roadie is ready, right? And so maybe this first part that process 2 is doing is some sort of setup, like set up instruments, and then once the roadies are done, they call signal, and then the musician, which is P1, can go past the wait, and then maybe they can call play music. Right? And so in this example, the roadies do their thing, they set everything up. Once they're done, they leave. They're done with setup. Okay, and then once they're done with setup, our semaphore is going to let the musician go play. Okay, cool. And so that's what that example is like, when we have one process waiting for some other process to do some work, generally some setup work of some sort. Okay, now what about, so we've gone through what if the semaphore starts at 0, what if it starts at 1, and what if it starts at some number that's greater than 1. But what if it starts at some number that's less than 1? Like, what does that even mean? This is weird. And I could not, for the life of me, find an example where this would be a good thing to do. In fact, in general, semaphores, the value of semaphores are thought of as being positive numbers. So you generally don't want to be doing this. Useful. So yeah, don't initialize semaphores to negative things. It's really hard to find a good example. I couldn't find a good example where this was good. However, a semaphore's value, because of our particular implementation, where if we go all the way back to wait, we're decrementing the value before we do our check, it can become negative. Can become negative during execution. So when exactly can this happen? What does that even mean? Let's go back to our room example. So we have a room, and then we have our guard, which is our semaphore. Okay, and let's initialize our sem's value to 3. Okay, and then let's assume, so because we initialize it to 3, we all know that means that at most 3 processes can enter the critical section, can be inside this room at the same time. So let's assume P1 calls wait. So wait is going to decrement the value of semaphore, sem becomes 2, and then we're going to check that 2 is greater than 0, or greater than or equal to 0, and because 2 is greater than or equal to 0, P1 can go in. 2 or 3. Okay, let's assume then P2, and now notice that the value of sem is 2, and that means that 2 more processes can enter, right? Because P1 is inside, 2 more can be inside until our max of 3. Let's assume P2 calls wait, then we decrement our value of sem, it's now 1, and P2 can be allowed to enter because 1 is not negative. It's greater than or equal to 0. Okay, one last time, P3 calls wait, we decrement our value to 0. This is still okay, right? Because 0 is not less than 0. And so we let P3 in, and that'll get us our max of 3 processes. So now, let's say P4 calls wait, we're going to decrement our value. So sum is going to be -1. We're going to check, is -1 less than 0? Just like we did before. Yes, yes it is. So P4 can't enter. It's going to have to wait outside. And remember, we associate it to this particular semaphore. Okay? Now let's assume we have P5 calls wait. We decrement our value. Sum is -2. We check if it's less than 0. Yes, yes it is. Because it is, P5 is going to have to wait. Now notice that at this point in time we have two processes waiting. At this point in time, and the value of sum is -2. So let's see, let's assume that process 3 calls signal. Signal is going to increment the value of our semaphore. So it's back to -1. We don't check its value. We don't check if it's less than 0 or anything like that. We just check if there's anyone we can unblock. Right? Because signal doesn't care about the value. It's always going to try to unblock a process if there is a process to unblock. There is. So P3 is going to leave the room, and P4 is going to be allowed to go in. Okay? And at this point in time, we only have one process waiting, which is P5. Okay. So now, you guys can see that if the value of the semaphore is negative, that's however many processes are waiting. Are waiting to enter the critical section. Right when it was -2, there were two processes waiting, P4 and P5. When we let P4 in, it increased to -1, and then there was one process waiting. Okay, cool. And that is all I've got to say about semaphores. This should give you, hopefully, a better understanding of what they are and how they work. For the purposes of your assignment, the key thing that I see many students forget is this association. Remember to associate or link when you block a process, you have to associate it with that semaphore, because you can have more than one semaphore. And each semaphore is going to have its separate queue of waiting processes. It's the equivalent of having more than one room, right? More than one guard for different rooms. And then the other key thing is if there are block processes for that semaphore, not for any of the other ones, you want to unblock one of them. So when you're testing this first part of your assignment, just make sure that you can handle more than one semaphore and that each semaphore can have more than one process just waiting at a time. And you can test out all these different initialization values now that you know what they all mean. Okay, cool. So hopefully that was useful, and good luck to all of you on the midterm.